Welcome to another physics problem with the physics tutor. Here we'll be tackling problem number 3 from chapter 11 in the Giancoli book. Problem number 3, which comes from the simple harmonic motion section again, reads as follows. An elastic cord is 61 centimeters long when a weight of 75 newtons hangs from it, but is 85 centimeters long when a weight of 210 newtons hangs from it. What is the spring constant of this elastic cord? Okay, so like any problem, the first place I'm going to start is I'm going to draw a picture so I can better understand what's happening. So that's essentially my ceiling. I'm going to imagine that these cords are hanging from the ceiling. Okay, and it's asking us about the quote-unquote spring constant of this elastic string. So in essence, what we're going to be doing is we're going to be modeling the string in this problem as a spring. So we're going to have some kind of spring, and it is pulled past its normal length because we have attached to it a weight of 75 newtons. Okay, be careful in this problem because they're giving us this mass that's attached to the spring. They're giving us its weight, not its mass. So we've already done m times g to get 75 newtons of downward force created by the gravitational attraction between the weight and Earth, stretching the spring out to a total length for the spring of 61 centimeters. Okay, we actually don't know how long the spring is when it's unstretched. That's not information that they've given us in the problem. They've simply told us that if we put a 75 Newton weight on this string or spring, it will be 61 centimeters long. Okay, so we don't know how much effect the 75 Newton weight has had on it. However, they tell us in the second part of the problem that if we have 210 newtons, we have 210 newtons of mass, or weight on this string, well, then it extends out even further. So now we have 210 newtons, and the string, it's the same one that we started with 75 newtons on. This now extends down out to 85 centimeters. Okay, so we have a change in the length of our string by adding more weight. We have a total change, a delta x. This new length of string is 24 centimeters. Okay, so essentially what's happened is we started with 75 newtons, and then basically what we did was we added 135 newtons to the 75 newtons to get a total of 210 newtons, and that caused the string to extend further by an additional 24 centimeters. So there's a couple ways that you can attack this problem, but the way that I'm going to think about it is I'm going to think about it as if we started with 75 newtons. So we start with 75 newtons, and then we add enough mass on to produce a force of 210 newtons on the spring to get this additional 24 centimeters. It's okay that we don't know the initial length of the spring. We can consider this to be equilibrium position 1, and this is equilibrium position 2. How do we move from 1 to 2? Well, we do so by adding more weight or more mass. We add 210 newtons minus 75 newtons. We get 135 newtons of added weight. Okay, so we're increasing the weight force by 135 newtons to go from equilibrium position 1 to equilibrium position 2. So what in fact caused this change? Well, it was the addition of that weight. So the way we're going to solve this problem is very much like how we solved the first part in problem number 2 when we looked at what the K constant was for the springs in number 2. So what we can say is that the sum of forces in the x direction to cause this displacement is going to be negative kx minus mg is equal to mass times acceleration, but recall our acceleration at this equilibrium position is 0. So this becomes negative kx minus mg equals 0. This mass is the added mass of 135 newtons, not the total. And I should say not mass here, but yes, well, this is the added mass that has a weight of 135 newtons, okay? This mass right here deals with this 135 newton change, okay? I realize I'm mixing mass and newtons here. Not really a good idea, but hopefully you're following the explanation. Okay, so this whole force right here, m times g, is our 135 newtons. So we're going to solve for k. So negative k is equal to mg over x. K is equal to negative mg over x. Our mg is the change in weight, the added 135 newtons. So this is negative 135 newtons divided by our change in displacement. We're going from here to here. We're going in the downward direction, so I choose down to be negative. So my change in displacement, 24 centimeters, I'm going to convert that to meters. So that's 0.24 meters, and that's in the negative direction. So 135 newtons divided by negative 0.24 meters is equal to 562.5 Newton meters. That is our K value. So K is approximately, let's see, they gave us 1, 2 significant figures, 1, 2 significant figures, 2 significant figures, and 2 significant figures. So we'll round this to 2 significant figures, which will give us 560 Newton meters for the correct answer to 2 significant figures. I'm rounding to 2 significant figures. This is exactly the same treatment that we used in the first part of problem number two, the car and the driver problem. I hope this explanation worked for you. Hope you got some value out of the video. Please like and subscribe if you're finding this useful. And of course, always enjoy physicsing, and I'll see you in the next one.